We are using micro-optical components like these thin film filters. And of course, we want to characterize the geometry of such little tiny pieces. And that's not that easy. You can't use standard microscopy or things like that. And if you want to find out how we do it, just stick around and we'll check it out. To characterize tiny little objects, which are highly reflective and basically plane, we are using a white-light interferometer. Now the question is, how does a white-light interferometer work? First of all, let's have a look at interference. If we have two light waves coming from the same source, they can interfere. And the result depends on the phase difference or the phase situation of those two waves. For example, if we take the two blue waves, which are perfectly in phase, if they are interfering, this means they are adding up. So the amplitude is doubled and the result is a white light. If we now take the second situation to combine blue and green, green is shifted by 90 degrees, we have a partially destructive interference, meaning we have kind of gray. And if we now combine green with red, they are completely shifted by lambda half. This means we have complete destructive interference, means the picture is black. Now the question is, how can we use this? Depicted here, you can see an interferometer. On the left-hand side, we have a light source, and one light beam or one light path is the light is hitting the beam splitter, is reflected down to a probe mirror, and the reflected signal is passing the beam splitter and going directly to the camera. This is the red path. If we now look at the green path, this means the light from the same source is passing the beam splitter, hitting the reference mirror, and on its way back, it's reflected to the camera. Meaning, the signals are interfering on its way to the camera. Depending on the length of the two paths, we have different signals. For example, if the red and the green path have exactly the same length, this means we have constructive interference, so the camera sees a white light or a white picture. If we're now shifting the probe at the bottom, so we are only changing the length of the red path, by the way, so we can have the situation that we have destructive or constructive interference or gray pictures or whatsoever. In this situation, we always have a homogeneous picture at the camera, at least when the two mirrors are perfectly flat. If we now put the beam splitter to the side, we can say they are completely perfectly parallel. And as you can see, the path has the exact same length at every position of this filter. The situation now changes if we tilt the probe. If we tilt the probe, you can see we have a very long path on the left-hand side, and on the right-hand side we have a very short path. And the result of that is we have destructive and constructive interference, and they are alternating, and we have all the different situations in between. This results in a picture for the camera, which looks a little bit like the sketch here on the bottom. So this means we have a black line, we have a white line, and the gray colors, it was not that easy to sketch here, but you can imagine this. By the way, depending on the angle of the probe mirror, this pattern here is a little bit denser or is a little bit wider. Now the question is, how do we use this to do a measurement of our components? To answer this question, let's go down to the clean room. Okay, now we are here in the clean room, and this is our brand new white-light interferometer. Although there are some microscopic lenses at the bottom, it basically represents what we have seen before with this interferometer. So this is the measurement head, the interferometer, and it can be moved vertically very precisely with a piezo or something like that. And here at the bottom, we have our sample, so the part we want to investigate. If we now look here, you can see the camera picture and you see the interference pattern. And if we start the measurement, the head is now doing pictures at every height. So we are slicing the height, and like that, it is possible to calculate the height profile or the profile of the surface, but because it's not a flat mirror surface as we discussed before, this is a real live surface with scratches and all that stuff. And the software translates this height information into color information. Here we can see the colors are going from reddish to bluish, so this means it's a scale of several hundred nanometers. And if you can see the cross section here at the bottom, so the end face is slightly curved, but it's also something with a radius of meters, I would say. And that's the reason why we can do such precise measurements. Now, what is the difference between interferometry and white light interferometry? We are using white light because the coherence length is very small. And like that, we have a good resolution in height. But I guess this is a little bit too complicated to go into details in this video. So perhaps it's something for the next video. I hope you learned something today. If so, please leave a comment and see you in one of the next videos. Bye-bye.